Okay, let's quickly start our chapter. See, we are starting with waves. Okay, we'll start with obvious questions and we will try and answer those questions with whatever knowledge we already have. Okay, so the name of the chapter is waves, right? What are waves? What do you think wave means?
Waves are like
This is a wave. So, but what is this? What am I doing?
uh,
What does constitute a? Okay, there is some movement in waves. Then, what kind of movement? Can you say something more about this movement? It is a movement. What kind of movement?
particles colliding with each other and moving.
Okay, there is also collision, right? What else? There is movement. This movement causes collision. So this movement carries on, है ना? So one particle will move, it will form a collision. This collision will move the next particle. This will collide with the next particle. This will keep on going further and further. This is what moves the wave forward. So basically, wave is a disturbance, है ना? Disturbance which produces vibrations. When we look at these vibrations, we are actually looking at waves. Makes sense? है ना? You're going to get the video. So this lecture, focus on what I am teaching and try to be involved. You can again look at the video and write whatever notes you want to write at home. है ना? You can take screenshots and make it a notes in your iPhone. Right. So what I was saying, that waves are disturbances. These disturbances make vibrations and these vibrations are what we see. Right. So if that is clear that we are actually looking at vibrations, I will then translate the how vibrations are waves. है ना? That will come in a short while. But let's, if with this in mind, let's understand that what can be the types of waves. Okay, so there can be two types of waves depending on their nature. Okay, nature meaning, do wave require material medium for propagation or not? For example, sound wave, है ना? Sound wave requires material medium. It can pass through solid, it can pass through liquid, it can pass through even gases, है ना? You can listen to me because sound wave can travel through gas. So these are known as mechanical waves. Okay, what is the characteristic? How do I know that it's a mechanical wave? Because it needs medium to propagate. Okay, right? You can also say by the way they propagate, right? Other waves are electromagnetic waves. Okay, electromagnetic waves. Example, light is an electromagnetic wave. We'll look at light in the next part of the chapter, right? So we'll discuss more about light, how light is a wave, but what is the property that it does not need medium to travel. Right. What has happened? That light travels from sun to earth. Right. There is no atmosphere. Right. All the way there is no atmosphere. There is atmosphere near the moon. Near the sun. Near the earth. There is no atmosphere in between. It's just space. Right. Still, these waves are able to travel. Right. On a lot of experimentation, we did come to a conclusion that they are electromagnetic, meaning they have electricity, they have magnetism, right? How is it moving? That we will see when we look at light. But it does not require any material medium. One more example of mechanical waves would be seismic waves, है ना? The earthquake, it travels because there is material medium. If there is no material medium, it cannot travel. As simple as that. So this is the nature of the waves, how they propagate, right? Now, other type of wave is looking at the vibration of particle. Okay, so see, let's take an example of a rope. Okay, if I wick a rope, okay, I'll show you a video now. If I wick a rope like this, what will happen? Right? The rope vibrates up and down, but you look at the wave that it is going forward. है ना? So between your vibration and the direction of progress of the wave, है ना, there is a right angle. Right? This is transverse wave. Okay? This is a transverse wave. Now, have you seen a slinky? Do you know what a slinky is?
Yeah.
Right? That round thing, you push it, or it's a toy, right? So let's look at slinky. Okay? So these are the rings of slinky, है ना? If you push it from here, what will happen? The rings will vibrate back and forth, है ना? And where the wave will vibrate? It will vibrate away from the source. In this, the vibration and the progress of the wave are parallel to each other. Because they are parallel to each other, longitudinal waves. Right? These are the 4 bifurcation that we know about waves. So sound waves are longitudinal waves. Electromagnetic waves are transverse waves. Okay, seismic wave is a transverse wave. So they can be treated individually. A wave which is a mechanical can be a longitudinal or transverse. A wave that is non-mechanical can be longitudinal or transverse. Right? There is no interrelation between that. Now, if that is understood, let's look at a small video. है ना? See, in this what they are going to do, they are going to show us both the transverse and the longitudinal wave. See, this is longitudinal. How does the compression travel from one end to another? That is longitudinal. Now they will show a transverse wave. See.
Okay.
Huh? This is a transverse wave. Let's look at one more example of how a transverse wave looks like and an important conclusion about the transverse wave. Okay, let's see. What is happening over here? The particles are made to vibrate. This is like a rope, right? And the wave is progressing from left to right. But if you notice this green bead, right? For that matter, any bead, but you can focus on green bead properly. What is happening to the bead? The bead is moving just up and down. Although it feels like the wave is moving, and actually the energy is progressing from the vibrator to the other end. It is definitely going in this direction, but the particle always moves up and down. So this will also be true for a wave that is longitudinal. If I am speaking, if I am saying sound is a longitudinal wave and I am speaking, what is happening? Particles, air particles that are in front of me will move like this, but this particle does not reach your ear. This particle makes other particle vibrate, that makes other particle vibrate, and the wave progresses. Right? It is clear from this example. Now if you have understood about green beads, you can also look at red beads. They are also not going forward. None of the particles are moving forward. All the particles are just vibrating. What is progressing? Energy. The energy that I have given from here is progressing along the way. It can be sound energy. It can be other forms of vibration. It can be an electromagnetic energy. Right? Light is a form of energy, है ना? So that being said, do you want to ask anything till here?
Yeah, I had a doubt that like how can you know that if it is a longitudinal wave or a transverse wave without me looking at it? Like how do you
So
know sound is longitudinal?
yes, so we don't know if sound wave is longitudinal or sound transverse. So what we did was we made a small experiment that okay, I want to find out if the sound wave is longitudinal or not. So to do that, we will design an experiment where we can look at particles vibrating. If those particles can be seen vibrating, I can conclude that it is
Transverse.
right or longitudinal for whatever matter it may be, है ना? So there are two experiments. One experiment is very known. I'll come to it the second. But let's say what I have done is I have kept a lot of sand particles on the base of this tube. Okay, this is a closed tube. There are a lot of sand particles on the base of this tube. Okay, and I have kept a speaker over here, right, which is emitting sound in this direction. What we observed was these particles slowly they move in a certain direction. Okay, what started happening was, let's say there was this particle over here. Okay, it moved like this and finally it settled in this position. So I had spread sand all over the base. After some time what I observed was there were a few points where there were some particles concentrated. Why did this happen is because as we have seen in the slinky, right, what happened was that this, whenever you push this, right, there will be a compression, there will be a lot of waves which stick together. We call this compression, right? And because the number of particles, right, are limited, it's not that we have unlimited supply of particles. So if somewhere compression is taking place, some place the particles are very far from each other, है ना? Very far from each other. What is this? This is the rarefaction. Okay, there is rarity of particles. Particles are less. So in this vibration, what happened was sound particles found a mean position. These sand particles found a mean position where when the sound was stopped, it would go and fall there. So this makes us believe that okay, sound is a longitudinal wave. But there is one more example. What you can do is you can take a speaker, right, and then you can add a lot of thermocol balls like this, right? Now this can be intuitive. Whenever if you turn on the speaker, the thermocol balls will move up and down. What direction is the sound moving? It is moving away from the speaker. What is this? This is a parallel. This is how we also can prove that sound is a longitudinal wave, right? There are a lot of ways to find it out, but for sound these are the simplest ones.
What about transversal wave?
So if we are talking about if we are talking about, let's say, electromagnetic waves, right? So it like there is a lot of formula and derivation to that. But in the simplest manner, we understood that electricity is a vector, magnetism is a vector, and propagation, movement is also, displacement is also a vector. They have to be at right angles to each other. They have to be at right angles to each other, which makes us sure that it has to be transverse. The simplest logic was this, but there involves a lot of derivation and formulas. Quickly, okay? Now, what was the next thing? Right. So we are trying to understand characteristics of waves. So see, if I am calling all of these things wave, right? There must be something common with transverse, longitudinal, mechanical, and non-mechanical waves, right? They must have something in common. Whatever common properties they have are known as characteristics of wave. If these things are present, then you are looking at a wave, right? It can be mechanical, non-mechanical, transverse, or longitudinal. But the wave will contain this, right? So let's start with something we've already understood, that there is compression and then there is rarefaction and then again there will be compression, right? If you look at a rope, right, this is how the rope would have moved, है ना? This is how the rope would have moved. Now this is known as crest, just like this is known as compression, this is known as crest, right? This is known as rarefaction, right? Over here this is known as trough. Okay, this is another crest and this is another trough. But how would I get? See, this is obvious that you take a photo of a slinky and you can find this. Here also you take a photo of this and you will look at this, right? But how can I also draw longitudinal waves like this? Because whatever waves we draw, that will look like this and a lot of calculations become easy, right? But what are those calculations? Let's first understand, then I will convert this wave to this wave. Okay, so let us first look at things. There is another, instead of taking a photo, there is a easier and better way. પેપર ચેક નથી થાય પણ અહીંયા પડ્યા છે.
કયા લખ્યું છે?
બાયો લખીશ
ગઈકાલ નતું લખ્યું
તો આજે શું લખીશ? કેમિસ્ટ્રી.
કેમિસ્ટ્રી
કેમિસ્ટ્રી મંડે લખ્યું.
ટ્યુઝડે કેમિસ્ટ્રી, મંડે ફિઝિક્સ, ટ્યુઝડે કેમિસ્ટ્રી
અને ફિઝિક્સ ચેક બી થઈ ગયું છે અને કેમિસ્ટ્રી
ના
બી
ફિઝિક્સ નથી ચેક થયું, કેમિસ્ટ્રી ચેક થયું.
તો કેમિસ્ટ્રી લખીને છે.
ફિઝિક્સ લખ્યું.
કેમિસ્ટ્રી. ઓકે, સો
22 નો ફિઝિક્સ કરનો બી ફાઇન કોઈ બી
કોઈ right, sorry. So let's, instead of looking at just this, let's make our own wave. Okay, do you know what is a pendulum?
Yeah.
Right, there is a string, string, right, and there is a weight attached to the end of this string. Now instead of attaching
કયું કયું
2 3 कोई भी कर दे, बाकी हो 2 2 ON बाकी हो तो ये कर दे, नहीं बाकी हो 2 2 ON में कोई भी बाकी हो ये कर दे,
ઓએમ ની વાત કરે મારે એમજી હશે
तो ये करिए. Right, so I am hanging this pendulum over here, है ना? Let's consider it like this, that I am hanging a pendulum over here. ठीक है? Then what I will do is I will, on this bob I will attach a pen. Okay, then I will disturb this bob. What will happen? The pendulum is going to move like this. With this, if I move the paper, if there is a paper behind, because I have placed a pen, and if I move the paper like this, will I get a wave like this? See, this is a pen, right? And it's continuously moving like this. So if the paper was not moving, the pen would make markings like this. But what if the paper was moving? The pen is moving like this, but relatively paper is moving upwards. What will happen? I will see something like this. Now what are these points called? They are not crest and trough right now. These points are known as extreme points. These are the points where the pendulum can shift maximum to. It cannot go beyond this. If I disturb a pendulum, it can go maximum to this point, and then it will come back on the other side also. It will go maximum this much, and then again come back. So these are extreme points, है ना? Let's say if there was a number line with this, so should I take my original as 0? Makes complete sense, है ना? In this side there will be positive, on this side there will be negative observation. Is it safe to say that this positive marking and negative marking are going to be equal if you ignore the sign? If this goes till +4, it will go on this side till -4. If you ignore all the friction, it will go from +4 to -4, +4 to -4, है ना? So these extreme positions are there. If you take an average of these extreme positions, what will you find? +4 -4 is 0. So the average, also known as mean, है ना? What is this line showing you? The center line is nothing but 0, but also known as mean position. If the pendulum was remaining undisturbed in vibration, if this particle was remaining undisturbed, it will remain at this mean position. Makes sense? But as it is the center, it is also known as equilibrium position. Both of these terms are correct to define this center line. है ना? Is this making sense? This displacement, this maximum displacement from the mean position is known as amplitude. है ना? And if I notice a time taken for the pen to start from here, right? Okay, start from here and come till here, right? This time is nothing but time period. Time period is denoted by capital T. Amplitude is denoted by capital A and it is measured in meters because it is maximum displacement from mean position. Time period is the time taken by one complete wave, है ना, to pass. But what is a one complete wave? One complete wave is the distance between starting of the first disturbance going from crest to trough or from one extreme position to other extreme position and coming back to the original position. But for us, the board has said, you know, I don't want you to take a lot of stress. They have said that don't think about extreme positions, right? They have said that think about something like this is crest and this is trough. So they have said you can add a crest and a trough and that is your one wave. But it is also true that from one crest to the other crest, if you find this length, that is also wavelength. Meaning the time taken by the wave to travel from here to here is also time period. Right? This is also wavelength. If this wave was continued till here, then the distance between these 2 points is also a wavelength.
Then sir, what is frequency?
एक second. Wavelength is denoted by the letter lambda. It is measured in meter because it is length. Amplitude is also distance. Wavelength is length. Both of them are measured in meter. Time period, because it is time, is measured in seconds. Makes sense? Now, if I want to write it down like this, can I say that oscillations and time? If I relate oscillations and time, can I write it like this, that one oscillation is nothing but time period? How much time does it take? Time period times. है ना? Then in 1 second, how many oscillations are taking place? This is known as frequency.
Okay.
So by the virtue of its definition, frequency is equal to 1 by time. 1 by t, 1 by time, both are correct. And the unit of frequency is hertz. H-E-R-T-Z. Makes sense? Amplitude, frequency, time period and wavelength are the characteristics of a wave. If these 4 things exist, it is a wave. Okay, this makes sense. Now should I convert this longitudinal wave to this kind of graph? Now do you understand that this is not a transverse wave. This is a trace of either a longitudinal wave or a transverse wave. But let us also look at how is it a, what did I say? It's a trace, right? So let's look at it like this. Okay.
So will the board ask the difference between transverse wave and longitudinal?
Yes. So you have to write that parallel and perpendicular. सामने लिख रही हूँ. आज रिवीजन करना है? पक्का? ठीक है. करो. पर मेरे को बोल के घर जाना जब भी जाओ. Okay. Yes, they will ask. So you will write that the vibration and the propagation are perpendicular or vibration and propagation are parallel. Right? That is it. What you have to write. Nothing else. Now this was compression, right? This was compression and this was rarefaction. है ना? What I can convert it to, compression is high pressure, so it corresponds a crest. This is low pressure, corresponds a
Trough.
between a rarefaction and a compression there will be a particle which is not moving. We can say that particle is actually on the mean position, right? Equilibrium position, correct terminology. And again there will be a compression which is a crest. This also will be continued just like this way. So I can use this one diagram because this diagram becomes, see, this is easily understandable, है ना? Now because I have showed you a video of Slinky, this makes sense. Otherwise this is gibberish, right? So it is always better to explain everything using this graph. Makes sense? Pakka? Now, can you tell me what is? Achha, we will keep on looking at this part of the wave for the next explanation. Can you tell me what is velocity? Definition of simple velocity that we know. Displacement upon time taken, है ना? Now let's talk about velocity in terms of waves. Okay, let's write velocity is displacement. So if I want to standardize displacement, I will say that okay, let's look at one wavelength because that is a standard length that we know of a wave. So I will write lambda. Clear? Time, the time taken for this much wave to pass is t, time period. This is velocity. But we have just found out that 1 by t is frequency. If I substitute this over here, can I write velocity is equal to lambda into f?
Yeah.
है ना? Because velocity in small box I'll write velocity is equal to lambda multiplied by 1 by t actually. So this 1 by t is nothing but frequency, है ना? And therefore this becomes my wave equation. Any wave, transverse, mechanical, non-mechanical, electromagnetic, transverse, non-mechanical, all the waves will follow this wave equation because it comes from the fundamentals of physics, है ना? Velocity is displacement upon time is true anywhere, है ना? Therefore the wave will follow this. This is a nature that we have plotted, है ना? Remember when we do a lot of formula in physics, the cause might get lost. Always remember, nothing happens because of formula. Formula is a mathematical representation of nature. And we have observed that this will happen. Is this understandable? Now let's take this formula and let's understand a few things. Okay. So the formula is V is equal to F lambda, where this is frequency measured in hertz, this is lambda measured in meters, and the velocity is meters per second because velocity, है ना? Now let's look at speed of sound. Do you know what is the speed of sound? Any idea? See, let's talk about air, water and steel. Okay, even if you don't know the value, can we predict that if the velocity of sound in air is 340 meters per second, will it be faster or slower in water?
Slower.
Why slower?
Because water is more denser.
So if water is more denser, right, let's think about it. Let's think about waves in the form of disturbance, right? There is a car where people are sitting with, they're not touching each other. If one person moves, will the person around that one person have to move? They don't have to.
No.
But let's say it is a crowded metro. If one person moves, does other one have to?
Yeah.
They have to. What does this mean? That if the density increases, the propagation of that vibration becomes faster.
Yeah.
So the velocity should be more, and in fact it is 1500 meters per second in water. Going by the same logic, it is 6000 meters per second in.
But the sound wouldn't be that clear, right?
So what will happen is, if I want to hear the sound, because my ears are naturally made to hear sound from air, that sound has to come from air for me to make sense of it. But there is something, what you are saying makes a lot of sense, because there is something that uses this undecodable sound. This system just wants to see if there is sound or not, and that is known as sonar, sound navigation, and what was it? Radiology. No, sound navigation and radar. Okay. Now, what is sonar used for? It is used by ships. It is used by submarines to find out distances. Okay. What kind of sound does this emit? Do you have any idea? Have you heard of submarines using sonar to find out depth of the sea, so they can find out how much they can sink?
Yeah.
Hannah, you also know that bats use what kind of sound? To guide. Bats are blind, so
Yeah.
they need guidance in at night
Sound.
for their flight. Hannah, what kind of sound do they use?
They sound.
Ultrasound. Do you know what is ultrasound?
Yeah.
What is ultrasound? If you cannot remember what is ultrasound right now, let us start with what is the range of human hearing. There is a range. Do you know that there is a range of human hearing?
Yeah.
Frequency. Hannah, what is this range? 20 hertz to 20,000 hertz. Okay. So if the frequency of the sound that is being emitted is beyond 20,000 hertz, I will not be able to hear it. If it is less than 20 hertz, I will not be able to hear it. Not me, any human will not be able to hear the sound. If the sound frequency is less than 20 hertz, it is known as infrasonic. If it is greater than 20,000 hertz, it is known as ultrasound. Ultrasonic or ultrasound. Ultrasound is used for sonographies, right? If you get hurt somewhere, or doctor wants to find out that inside your skin, without puncturing your skin, without making any cuts, if they want to look at blood flow, if they want to look at your tissues, ultrasound can be done, right? I hope ultrasound in this context you know, right? Now, this same ultrasound can be used by submarines. What will they do? They will send a signal, right? The signal will be reflected from a obstacle. It can be a fish if it is large enough. It can be seabed. Whatever it is, the sound will be reflected, and they will detect this sound. This is how it works, right? We will look at how does sonar work and how do they calculate distance after a few topics, because I would want to teach you how does sound travel, how to find out this distance, all of those things. But my question over here is, let's say that the ultrasound has a frequency of 25,000. This sonar uses a sound of 25,000 hertz frequency, right? The frequency of a vibration can be controlled only at source. Once the vibration is made, throughout wherever it propagates, it is not possible to change its frequency. Frequency is constant, right? In our topic 6, space, we will see that some things change frequency. We will also look at why it appears that frequency has changed. Frequency actually never changes, right? This is universal truth, because once that vibration is made, there is no way to change that vibration, but if the speed of sound in air is 340, right? can I write down two more formulas that if V is equal to F lambda, can I write lambda is equal to V by F and F is equal to V by lambda? All of these make sense? If these make sense, can you use your calculator and help me find out what will be the wavelength of the same sound in each case? How will we find out? Lambda is equal to V by F. So 340 upon 25,000, 1500 upon 25,000 and 6,000 upon 20. Can you tell me all the answers?
Uh, 0.0136.
0.0136 meters per second?
Is it hertz and meters?
Meters. It is wavelength.
We cannot write hertz, right?
No, because it is wavelength. We will use unit meter. Next answer 0.06 and this is
0.24.
0.24. Can you tell me what is happening if frequency is constant? Let's have a look at this equation, okay? Frequency is constant, but whenever velocity is increasing, what is happening to the wavelength? Velocity has increased. Velocity is something. Now velocity has increased. What has happened to wavelength?
It is increasing.
This is 1 and this is 6, which is a larger number. So it has increased. Now, if the velocity increases, what has happened to wavelength? Again. So can I say velocity and wavelength are proportional to each other? If, see, this same sound wave travels from air to water to some solid or reflects back, right? What can change? Both velocity and wavelength can change, but what cannot change? Frequency. What is relationship? They are directly proportional. If velocity increases, wavelength increases. If velocity decreases, wavelength
decreases.
Does this much make sense? This is what we have done in class for waves. If all of this makes sense, you can get up over here, you can scroll the board, right? You can go through the topics again. If you have any doubts, you can ask me right now. If you have time, you would like to make notes, you can make notes right now. I will scroll up for you. Okay?